Hi everyone, I am Ana Serrano and I am presenting our work The Effect of Shape and Illumination on Material Perception, Model and Applications. So why do we care about material appearance perception? Because material appearance is a core topic in computer graphics. Realistic materials are a key element for a realistic appearance, and this requires modeling the diversity and complexity of materials in the real world. This is a very challenging task, and understanding how humans perceive appearance can help us achieve increasing levels of realism. This knowledge can be useful for many different applications, such as creating more realistic video games or movies, simulating the appearance of car paints, or facilitating appearance reproduction in 3D printing or textile design. Despite much research effort, material appearance perception is far from being fully understood. But what makes material perception difficult? One of the reasons is because it involves many factors which are hard to measure and quantify. The final appearance of a material does not only depend on its reflectance, but also on the illumination of the scene and the geometry of the object presenting such material. For example, here we can see a semi-glossy pink material under the same illumination, but in different geometries. In the image on the right, this material looks more glossy than on the image on the left. The same happens if we change the illumination. In this case, we use again the dragon shape, and now the same material looks much more glossy on the image on the right after changing the illumination. Many works have actually studied in the past the impact of shape and illumination in material perception. Unfortunately, these works are usually very limited in the variety of appearances, illuminations, and geometries they study. Additionally, these works often focus on different subsets of these factors, making it difficult to compare them and generalize their insights. There is also a large body of work devoted to investigating the perceptual properties of materials. However, most of these works focus only on a single aspect of appearance, such as gloss or translucency. Finally, some more recent works study a wider variety of appearances, but do not take into account the effect of illumination and geometry. While studying small subsets under controlled setups is a necessary and valuable step for understanding perception, we believe that collecting and analyzing a large-scale collection of diverse appearances is crucial for generalizing existing knowledge and bringing insights closer to real applications. So with the goal of understanding and modeling the effect of geometry and illumination on perceived reflectance properties, the contributions of this paper are as follows. First, we have created a dataset of perceptual ratings for different appearance properties with more than 42,000 images displaying distinct combinations of material, shapes, and illuminations. Then, we have performed an extensive statistical analysis of the collected data, and we have discussed our observations with respect to existing knowledge in the literature. We have also used this large-scale dataset for training an attribute predictor that allows for estimating appearance properties from general 2D images. And finally, we have demonstrated how this predictor can be useful for many different applications. Okay, so let's see first what does this dataset contain and how did we collect it. Our dataset contains 520 different measured materials. We collected these materials from different databases, including materials from the Merle, RGL, and UTIA databases. When looking at the pool of materials from these databases, we noticed that many of them are fabric-like materials with very few reflections. So in order to compensate a bit this bias, we used the recent work of Sun et al. To obtain some new materials by performing color and reflectance edits on existing measured materials. And then we completed our dataset with the results. Our dataset includes 9 different real-world illuminations. For selecting them, we took an initial pool of more than 400 illuminations and made our selection aiming for variety in the frequency content of the images, as well as presence of both indoor and outdoor scenes and different types of light sources. For selecting the 9 shapes for our dataset, we aim for variety in features and complexity, and we also included shapes typically used in material perception studies. After this selection, our dataset contains more than 42,000 distinct images with different materials, shapes, and illuminations. Next, we based our choice of attributes for describing material appearance on existing literature. First, we include glossiness, lightness, and metallicness, since recent work has suggested that these are the main perceptual dimensions of diffuse and specular reflectance. Then, previous works have suggested that the 2 main dimensions of perceived gloss are related to the distinctness of image gloss, or sharpness of the reflections, and contrast gloss. So we also consider these 2 attributes. And finally, since we are including anisotropic materials in our dataset, we also add this attribute to our list, and this yields a total of 6 attributes. Now, all that remains is to actually collect perceptual information about the attributes we have selected for each of our images. In order to do this, we perform a crowdsourcing study on Amazon Mechanical Turks. We ask participants to rate in a 7-point Likert scale each of the 6 attributes for each given image. In order to deal with noise and improve robustness of the data, we included descriptions of the attributes and a short training with different examples for anchoring the scales. Each survey contained 20 random images from our pool, plus 3 control images for discarding unreliable users. In total, more than 3,000 participants took part in our study, and the outcome of this study were more than 200,000 valid responses, from which we also ensured that at the end, each image had at least 5 views from different users. From this data, we perform an extensive statistical analysis on the effects of illumination, geometry, and their interaction on perceived reflectance properties. In the paper, we connect our findings to different image statistics and discuss our insights with respect to existing knowledge in the literature. So if you're interested, please check the paper. After the analysis, our data confirms previous findings, suggesting that simple image statistics cannot explain all the observed variation in perceived appearance. Therefore, we use our dataset to train a simple architecture that allows for predicting material appearance properties from 2D images. First, we take out all images containing the bunny shape and one of our illuminations, since we will use them for evaluating our predictor. Then, the remaining images are augmented using different augmentation operations. We ensure that a significant region of the image was still visible after the manipulation so that the perceptual ratings would be still representative of the images. We use a BGG16 architecture, and since we are interested in regression and not classification, we remove the last layer of the network and introduce a fully connected layer which outputs a 6-dimensional attribute vector. Since we are interested in predicting continuous attributes from each image, we use the mean square error as a loss function. We actually tested different architectures and loss functions, so if you are interested, please check the paper for more details. Then after training, for testing our appearance predictor, we use mainly 2 test sets. The first one, which we call evaluation set, consists of the images with the bunny geometry and one of our illuminations, which we didn't include during training. We also created a second test set, which we call extrapolation set, with more challenging images, including new materials, analytic BRDFs, and a few real pictures. We computed the mean absolute error between the predicted attributes and the ground truth ones, and these are the results. Overall, our predictor performs well in predicting appearance from general 2D images, and we can see that the errors slightly rise for the extrapolation set, but this is mainly due to some failure cases that we have identified and we will discuss later. In addition to these evaluations, we also performed several tests introducing changes in viewpoint, geometry and illumination complexity, and using different tone mapping algorithms in our images for checking the consistency of our predictor. Finally, we also tested our predictor extensively in real images using the materials in context dataset, and all these results can be seen in the paper. So now let's see some results of our predictor. Here we show an example of our predictor capabilities in rendered images. In this case, we are visualizing all our evaluation dataset as a function of the predicted glossiness in the x-axis and lightness in the y-axis. And all the predictions are in the range between 0 and 1. We can see how the predictor is consistent in its predictions, creating embedding with increasing perceived glossiness and lightness. Let's see now some more examples in real images. We are going to see a similar embedding, showing predicted glossiness values in the x-axis and predicted lightness in the y-axis, ranging from 0 to 1. We tested several material categories from the materials in context dataset. For instance, here we can see examples for the fabric category. The two images in the bottom are darker materials with low glossiness values. We can also see a brighter and slightly more glossy white fabric on the top left corner. And finally, we can actually see here a failure case. The yellow fabric on the top right corner. In this case, our predictor is saying that this image is quite glossy, while it is not, it's completely matte. And these results suggest that our predictor is kind of interpreting the white pattern as highlights and incorrectly producing a high glossiness score. In general, all the fabrics we tested get clustered around low glossiness values, which is in accordance with their actual appearance. Here we can see some examples for the leather category. On the bottom, we can see two dark samples with different glossiness values, and on the top, two slightly brighter samples with quite high glossiness values. Overall, the predictions match the appearance of the samples, and for the leather category, most of the samples get clustered around low lightness values because they are quite dark, with varied glossiness. Here we see examples for the plastic category. And in this category, most of the materials we tested show very bright colors, so they usually cluster around high values of lightness. We can see samples with low glossiness values, such as the yellow sample on the bottom left corner, and some other samples with quite high glossiness, such as the red sample on the top right corner. Finally, let's see some more examples for the category with metals. In this category, materials usually cluster around high glossiness and lightness values, since most of them are quite shiny and bright. And overall, we can see that our predictor is quite accurate in matching the observed material properties for real images, although we have clearly identified some failure cases. As we have seen before, one of the failure cases we have identified is related to real images with strong patterns, such as these two fabric elements in the image, which are incorrectly predicted as medium glossy. In these cases, we believe that the gradients produced by the cloth patterns interfere with the prediction. In general, real pictures displaying uniform materials without strong patterns work better for our predictor, since the images used during training were rendered with uniform materials. We have also found that in general, our predictor cannot produce reliable predictions for anisotropic effects. The predictor is able to produce medium or high ratings for anisotropic materials, for example, the two images on the left, but it also produces high values for anisotropy for similar but isotropic materials, such as the image on the right. Unfortunately, current datasets of measured materials do not contain a lot of variety of anisotropic appearances, and usually these effects are very subtle and usually best viewed under viewpoint changes. So at the end, our data is actually a bit biased towards isotropic appearance, and in this case, larger datasets of measured anisotropic materials could translate into improvements of our predictor. Finally, let's see some applications that benefit from our predictor. First, let's see how we can use our predictor as a distance metric for gloss reproduction in 3D printing. Our goal is to find the optimal varnish that best matches a desired gloss for a target shape and illumination for applying this varnish to a 3D printed object. In order to do this, we print a test object, in this case a cylinder, and apply our available varnishes. Then we capture the resulting BRDF. With this, we create a varnish collection. Then, once we have selected a target shape we want to print and an estimated illumination, we render the varnish collection in this shape and illumination. And this allows us to have an approximate image of how the varnish would look when applied in such conditions. Finally, we need to find the varnish that best matches the desired gloss. In this case, we want to print and varnish a dragon that looks as glossy as the red plastic toys on the right image. So we use our predictor as a distance metric, and we compute the glossiness of the image on the right and search for the varnish in our collection that looks as close as possible in terms of gloss. Here's another example. In this case, the dice looks less glossy than the plastic toys before. Therefore, the selected varnish also looks less glossy to match the target appearance. In our second application, our goal is to be able to edit materials by integrating our predictor into a differentiable rendering pipeline. In particular, we use Mitsuba 2 for this task. We start from a target geometry and illumination and measure material, which we can fit to an analytic BRDF. After the fitting, we obtain a set of reflectance parameters, which we will use for rendering our material. First, we render the image using the differentiable renderer. Then, we run our attribute predictor in the resulted image and obtain a set of attribute predictions. In this case, we focus on editing gloss, so we compare the predicted gloss with a target gloss. Finally, we use the difference between the predicted and the target gloss as loss function and backpropagate the error to update the BRDF parameters towards the goal of converging to the target gloss. Let's see an example. This first animation shows the convergence of the differentiable renderer using our predictor for fitting a measured material into an analytic BRDF. Okay, then we can edit this material and make it look less glossy. And this animation is now going to show how the BRDF parameters converge to produce a target glossiness of 0.1. And now we can also make it look more glossy. In this case, the achieved glossiness is 0.9. We can do the same for different target illuminations and geometries, and the resulting parameters will slightly vary to produce the desired glossiness, taking into account the effect of illumination and geometry in the final appearance. We also demonstrate some more applications, such as material recommendations for scene design, dataset sorting following material properties, or illumination design. Please check the paper if you are interested. So to conclude, we have presented a study on the effects of geometry and illumination on perceived appearance. For this, we have first collected a large-scale dataset and extensively analyzed our collected data, connecting our findings to those of the previous literature. We have trained and thoroughly tested a predictor that allows for predicting appearance attributes from general 2D images. And finally, we have shown that this predictor is indeed useful for many different applications. With this, I conclude my presentation, and if you are interested, you can find our dataset, predictor, and code available in this link on the top of the slide. Thank you for your attention.